Hi, my name is David Carson, and I'm presenting my PCB project for EE309 Junior Laboratory 2. My design is for a Wi-Fi sounder device. These days, RF communications are vital. Everything's going remote and wireless to connect new devices coming out to the cloud, as an example. These devices, for the most part, operate in the 2.4 gigahertz spectrum. The FCC has designated this for industry, scientific, and medical purposes, and it is unlicensed, so you do not require a license to use. This makes it very attractive for new designers to develop new devices utilizing them. However, along with that, there becomes the risk of interference and noise. And my design was to enable one to be able to check and see how much noise there is on a given channel at a given location. Now, my device uses an XB radio for RF communications, a PIC microcontroller for controlling commands to the XB unit and sending responses, and then just beyond that, it's just basically a power interface, as I'm taking a 9-volt battery source and I need to supply a steady 5 volts to the microcontroller and to the XB unit. Here is my final PCB. You can see down here the XB RF unit, and if I tilt it, you could probably see it's got a small antenna on it here. The PIC microcontroller is up here. It's the 18F4520. We've got the voltage regulator up here, our resistor network, and I will get into some caveats about this design. So, unfortunately, my final PCB is non-functional. So I would like to describe some of the things that I've learned during this lab, because the design phase is very important. And when I began prototyping to simulate my design, I ran into an issue with the RF device to use. Now, we were to use non-surface mount components. I had found another chip by Texas Instruments, which was a surface mount, so I could not use it for the design, but they did send me a sample for educational research. So I went with the XB units, as they have pins that you could insert into into a board. So the issue that I ran into, however, was using multisim. It took considerable time to figure out how to create a new device that I could interface into my circuit, because XP is not a standard unit in their libraries. However, having gotten that far, I then couldn't export to Ultiboard because it had no idea what to do with that, and that was where my time and experience came to a halt. So I went with Eagle, which actually had a XP component in their library. So I was able to do the schematics and Gerber files, the board files, and generate Gerber files using Eagle. However, by this point, I was really short on time, and I hadn't tested the configuration. And in order to make sure that I received my PCB in time for the project, the call was made to go ahead and submit the design, and that was high risk and proved a couple of points. One, you really need to spend the time up front in order to ensure that your design is going to be successful. When you're working with manufacturing windows, you miss your window, you can't just resubmit and basically have a do-over. You no longer have time for your deadline to receive your final project. This is the case here. So those are some key critical lessons to learn in doing this project and this design. However, what I learned since submitting the design, in order for this project to work successfully, is I was able to actually work very successfully with this configuration. I needed to make a couple of changes to my original design. First, the voltage regulator and the power interface circuit, that actually worked well. And so I was able to get a steady 5 volt from my 9 volt battery. However, the XB input pins, and it outputs and inputs at 3.3 volts, not 5 volts. It can take 5 volts to power the device, but its communications are all 3.3 volts. The PIC, of course, is all 5 volts in its inputs and outputs. So what I ended up doing was implementing a voltage divider. So the output from the PIC would go through the voltage divider with a 2-to-1 ratio. Made it very easy to get 3.3 volts out as 2/3 value of 5 to the XB. That worked wonderfully. Taking the 3.3 volt, I then used a level shifting circuit to bring it up to send to the PIC. And all that ended up working quite well. So with the final design, I'm able to take this unit and turn it on by supplying power to the device. And I could place it in different places, and it will report back to computer via Wi-Fi the RSSI that it has at those locations. For my project, I selected 4 locations in my house, which is where I'm doing this this video, and right here in my office here, in another room at the other end of this floor, and then the 2 locations on the lower floor downstairs. And I was able to then graph and chart. I tried 3 different channels, and I went with ones that did not overlap for to reduce interference. So channels 1, 6, and 11 were used and tested at each of the 4 locations, and then I charted the results. And from my tests with this device, channel using the breadboard circuit, which is actually right here. I have the 9 volt battery. Another PIC here. Oh, and this down here is a breakout board. Let me pick that up and actually show it to you. Now, the XB unit, this was the other issue that I came across in this project. The XB unit itself has 20 pins, 10 down each side, that are too close together to insert into a breadboard. So I couldn't test my design on the breadboard circuit either. That was the other challenge that I had in getting tests done before I could. I had to submit the Gerber files for manufacture. So what I ended up doing was ordering a breakout board. Now the breakout board has these where you can insert the XB unit. 10 pins here, 10 pins there. And it takes, it has these holes in the bottom. It even has them labeled. I don't know how well you can see that. Apologize. It labels the ground 3.3 volt, D out, D in, and so forth. And it has these pins for a holder that are perfectly spaced for inserting into a breadboard. So with that, I'm able to insert it into the breadboard. And then from there, it was a matter of making the connections so that I could communicate between the PIC and the XB unit. I also tested the interface with the PIC DEM 2 board, which I had left over from another class. This provided me with serial output, so I could actually log the data I was getting to the PC. And I was also able to output to the LCD so that I could see the RSSI values and further test the communications between the devices. It worked rather successfully. I was quite pleased with the results. However, as I said, the key thing is what I learned as far as ending up with a non-functional final PCB project. This is my final board, David Carson, and thank you.